Hello, everyone. Oh, hello, everyone. I'm Arush, and I'm here to talk about a powerful new tool called Gandhiva, introspective cluster scheduling for deep learning. So, about our project, we're going to start off with GPUs. We use big cloud computers to train AI. However, when lots of teams share the same computer, things get slow and quite expensive. We can think of it like huge shared kitchens. And the reason for it being slow and expensive would be the computer's manager, the scheduler, is blind. It basically shows it throws jobs at any free resource. Gandiva gives the manager eyes so it can look inside each job to see exactly what it needs so it can make smart and tailored decisions. This paper that I read, it really shows the ways that blind scheduling wastes our time and money. And yeah, let's see how Gandiva fixes them. So we can see here figure one. It shows a huge speed bump. It's just based on placement. Even on the same server, the connections between GPUs aren't all equal. Like we can see here the VGG16 model. If the scheduler places it on on the slow internal wires, like different sockets, the job it instantly loses 40% of its speed. Gandhi fixes this by being wire aware. It checks the map first and then puts all the jobs, GPUs, on the fastest, most direct internal connections. Here we have figure two. Figure two addresses what happens when jobs get split across different physical machines. So to keep the cluster busy, the scheduler often breaks one big fast job into small pieces and spreads them out. This makes the job slower and you lose a lot of throughput. So if you ask why, it would be because the network is slow. Talking between two machines takes way longer than talking inside one machine. Gandiva is dynamic though. Like it allows the jobs to be split temporarily for flexibility, but it never forgets. It's like it actively watches for a free spot and moves the pieces back together onto one fast machine to recover the lost speed. Figure three. Figure three shows the ultimate efficiency trick, like running two jobs on one GPU, which is called job packing. It's like if you pair two jobs that both need the same exact things, they interfere and fight. You lose 20% of the speed, and that's a fail. But then here's the genius part. If you pair two complementary jobs like GNMT and ResNet 50, right here, they run perfectly fine together. It's like Gandiva's eyes, the introspection allows it to profile these jobs and figure out exactly which pairs are safe. By only running these safe packs, it gets 25% more utilization out of the same hardware without slowing anyone down.
You can start. Figure 4, an IC interference. This figure is it's needed some explanation. It's a display the normalized performance of 3 deep learning models. That's we can see in the figure a ResNet 50, and then Inception V3, and then deep speech as the number of simultaneous jobs increases. The chart Y axis represents the performance relative to the baseline, where the X is a group, the model, and it shows the performance for 1, 2, and 4 concurrent jobs. And based on the chart, and we can explain the different components that I can start with ResNet 50 shows the highest overall performance and the least degradation as the number of jobs increases. And this ResNet 50, it's normalized the performance remain above 0.70. We can around that at 0.75 with 4 jobs. And then we have to talk about again, Inception V3 experiences a more significant drop in the performance with multiple jobs. And then this part is decreasing to around 0.5 when running for 4 jobs. This fish is most affected by the increase in jobs. It performs jobs sharply, reaching approximately 0.5 with the 4 concurrent jobs. And then the data suggests that the deep learning models performance is impacted by NYC interference, and that this effect becomes more pronounced as the number of jobs running simultaneously increases. Different models exhibit different levels of silence to this interference. Now we have to come back to ResNet 50 is the convolutional neural network. I think that's the purely technical words often used for image classification. While Inception V3 is also a CNN, this designed for image recognition, deep speech. There is a speech to next engine. So basically, we can explain the figure 4 with increase and decreases of jobs. So I think we can pass to the next class if you're ready.
You're on your second slide.
What's that?
Okay.
Now we are talking about the figure 6. We call it GPU usage options in Gandivar. Now we can give some explanation to Gandivar. By the definition of Gandivar is a cluster scheduling framework for deep learning jobs that improve GPU utilization and efficiency by exploring. I'm sorry, it's not exploring, it's exploiting the intra jobs predictability of deep learning tasks. Unlike traditional schedules that allocate GPUs as a one-time event, Gandivar continuously monitor and optimize the job placement. The image shows several GPU uses opportunities and technical use by Gandivar to manage jobs and then improve resource utilization. And then we can explain some parts. We can see in the figure suspense, resume, parking. And we can see again migration, and then we can see grow shrink. Now to come to explanation of the different parts of the figure that I just listed now, we can start with suspend, resume, or parking. This method leverages intra-job predictability to suspend and resume jobs when their GPU usage is at its lowest. It also allows multiple jobs to be packed and onto a single GPU simultaneously, assuming they do not interfere with each other. Now we have to pass with migration. Migration in Gandivar can dynamically migrate jobs to better fit GPUs, which helps to improve cluster efficiency. This can include moving time-sliced jobs to nearly vacated GPUs or relocating, interfering jobs away from each other. Now, grow shrink, the number of GPUs assigned to a job can be increased during a period of low cluster, lower and reduce when the demand for resources increases. This allows Gandivar to make use of space, resource, and then they shrink the job allow as needed. So as a conclusion, this is the brief explanation of figure 6. Figure 7 is we can call it a scheduling example in 16 GPU cluster, and we can see some explanation on this figure. The image shows a diagram titled Figure 7, scheduling example in a 16 GPU cluster. This diagram illustrates how the Gandivar scheduling framework distributes job across multiple servers and with different GPU configurations. Gandivar is a cluster scheduling framework and designed to improve the legacy and then efficiency of training deep learning models in GPU clusters. It addresses the challenges of deep learning and class loads by exploiting extra job and predictabilities. And where deep learning jobs consist and of repetitive mini-batch iterations with similar resources usage. And the key feature and the mechanics of Gendiver include time slicing. Gendiver uses intra-jobs predictability to efficiently time slice GPUs, allowing multiple jobs and to share a single GPU and reducing legacy. And then when talking about the migration, it can dynamically migrate the jobs to better fit the GPU, which helped and to improve cluster efficiency and utilization. This can be treasured by job departures of 4-day fragmentations. And packing, now we have to talk about packing Gendiver. That's can run multiple jobs on a single GPU simultaneously, particularly when jobs have low memory and a compute utilization to improve overall resources use. And introspection, the scheduler uses this introspection can be explained by the scheduler uses profiling of mini batch progress to continuously monitor and then optimize job placement, which helps in increasing cluster and utilization and reducing job completion time. And then we have two models. The two models can be explained again, and the scheduler operates in a reactive model for handling and events like a job arrivals, and then an introspective mode for continuous optimization of job placement. So basically, this we can explain the figure 7 with the previous explanation that we just gives to the figure now. Thank you.
So in figure 8, we have job migration in a shared cluster, which means that GPU slots can freely migrate, which is shown in the purple with the purple arrows. And then we also have other slots, job 0 slot and deep search slot. Each row has a server, and the yellow jobs are active, the green jobs are the deep search, and the circle X's are other jobs. Migration idles the GPU and it fragments, which makes it slow down, but it also helps increase the GPU affinity between multiple jobs. And it also helps boost cluster efficiency without having to wait for full rescheduling. In figure 9, we have time slicing with six 1 GPU jobs on 4 GPUs. We have 4 longs, long 1, long 2, long 3, long 4. And we have 2 shorts, short 1, short 2. And we have net throughput, which is pretty much the average time the GPU is going, how fast it's going. And we also have on the x-axis, we have mini batches, which is every 6 minutes. We have on the y-axis, mini batches per 6 minutes, and then x-axis, we have time in minutes. And fair GPU sharing, pretty much time slicing allows fair GPU sharing high resource utilization, and minimal throughput loss, which means the GPU won't really slow down as we're trying to split up multiple jobs at the same time. And jobs are not killed, they just pause so other jobs can go faster and take over their part. For figure 10, we have packing jobs on a single 40 GPU. We have two different graphs. One is packing and one is the core GPU stats. For the packing, we have job 1, job 2, and net throughput. And then the y-axis is in time in minutes, which goes up to 50 minutes. And for the y-axis, we have mini batches every 30 seconds. For the GPU stats, we have GPU memory utilization for the y-axis. And for the x-axis, we have time in minutes. Job packing pretty much allows jobs to run on one GPU to boost utilization instead of spreading it out. And it also allows us to show GPU memory and compute multiple things simultaneously, which also helps speed up the process. We also have GPU utilization, which actually rises as more jobs are packed. So on packing job 1 and job 2, the net throughput rises because the GPU utilization rises because more jobs are packed to do the same thing. And that's exactly why the memory of the GPU rises as well for the GPU stats. Overall, GPU allocalization is very useful for everyday tasks as it helps us handle multiple processes efficiency. Let's say if you want to open Zoom, you want to open PowerPoint, Microsoft PowerPoint, your computer won't really slow down. It will be able to handle multiple jobs at the same time. And proper GPU allocalization allows us to match this task faster and improve overall performance when we're doing things. That end, and thank you.